Welcome to Tetryonics. In this lecture we'll be covering the quantum geometry of the mass energies of all spectral lines. That is the colors or the photons that are emitted from electrons as they transition within the atomic nuclei. This lecture forms part of the series based on Tetryonic ebook number 2, Quantum Electrodynamics. And it's available on both YouTube and Google Plus, or upon request directly. Again, quickly recapping with Tetryonics, all mass-energy-matter geometries are equilateral geometries at their quantum foundation. That is to say that the square numbers of quantum physics are in fact the result of equilateral energy geometries. Alternatively, the measurement of energy geometries per unit of time gives us a measure of mass. So mass energy is equivalent as related through Einstein's equivalence formula, E equals mc squared. And we'll show in the course of this that it is the charged equilateral geometries of mass energy that form the three-dimensional geometry of all matter, and it is the energy content of these charged fascia of matter that gives us our measurement of mass. Obviously, the main departure between current quantum theory and Tetrayonic theory is the difference in where it relates 4-pi geometries to tetrahedral geometries as opposed to spherical geometries in the current quantum theories. This is a marked departure for quantum theory, and again it's based on the fact that equilateral geometries of energy form the square numbered quantum energy levels. In both cases they are 4-pi geometries. There is no distinction so far as the geometry is concerned, save for the fact that one is a spherical geometry and the other one's tetrahedral. In fact, it's this tetrahedral quantum of matter, the tetryon, that lends its name to Tetrayonic theory. A number of the formulations for geometry within the mathematics of quantum theory still apply, but obviously the physical geometry changes from spherical to tetrahedral geometries at the quantum level. These squared energy levels are formed through bosons interacting via the weak force, as illustrated on the left hand side of this page. All bosons are odd numbered energy quanta. That is to say, we have in both cases n Planck quanta, hence the formulation E equals nhv, which now relates specifically to bosons. Where it refers to energy, it would be E equals h nu squared. But in the case of bosons, we have n quanta, and they always add up. They're always odd numbers. Obviously, in the geometry itself, with an odd number, you'll always have a situation where there will be an imbalance between the positive and negative charges of the Planck quanta themselves. And in doing this, when the odd numbers form into the boson geometries, you end up with a charge, a net positive or negative charge, and in fact this is what's termed plus or minus W bosons within quantum theory. Again, they're illustrated as you see here. The only difference in the geometry is where you have a quanta of 1, a 0-point field. Obviously 1 is an odd number, so again it is a boson, but it's more correctly termed a 0-point field, as it's the quantum of bosons. These odd numbered quanta come together as illustrated on the left hand side of the scalar energy field And as they come together to form larger and larger equilateral energy geometries or scalar energy fields, they add up sequentially to give us the square numbers that are familiar to all people doing quantum mechanics. In this case, 1 and 3 make 4, which is 2 squared. 4 plus 5, or 1 plus 3 plus 5, gives us 9, which is 3 squared, and 9 plus 7 will give us 16, which is 4 squared. So as we've noted before in Tetryonic theory, square numbers in physics are not square geometries. They are triangular geometries, specifically equilateral triangles. And again, quickly, if you were to count the quantum number in a longitudinal fashion as opposed to the transverse fashion of bosons, you would again determine that the equilateral geometry in fact creates a bell curve or a normal distribution of energy quanta within its overall equilateral geometry. Again, the geometry in Tetryonics is simply shown as a pi geometry, pi radians, 180 degrees within the equilateral triangle, and it is the bosons that form the quantum levels of these scalar energy field, mass energy fields. Tetryonic obviously applies a color coding to these scalar energy fields, and this color coding follows the spectral colors. This is done for a deliberate reason, as will become apparent in this discussion, where we're looking at these spectral colors and the energy levels of various elements. Obviously the color code ranges between red for the lowest number of 1 through to black for 9, and this can be repeated again in different intensities to follow our decimal system of counting. But in all cases, the equilateral geometry have a specific geometry of odd numbers down the left hand side, square numbers down the right hand side, and the height of the triangle forms the square root reflective of the momenta of the energy field. So we can see the energy momenta, we can see the bosons as a transverse mass, and we can see the normal distribution of these quanta as a bell curve based again on their equilateral geometries. This n number arrangement is denoted throughout Tetryonics, obviously, because it's this geometry that forms the basis of all mass, energy and matter geometries. And in doing so, we simply change from n to nu or v. In both cases, the v or the nu are equivalent. One is determined by the other. The velocity of any field relies on the energy quanta within that field. And again, they're color coded. In the case of ordinary Tetryonics, the grey n will become a pink n or a fuchsia n, representing the velocities of particles or fields. The n squared is a maroon color, representing the energy content, and on the side here we have orange color coding to represent the fact that n quanta or odd quanta form charged bosons. Obviously, these equilateral mass energy geometries have a charge due to their equilateral geometry, which can be represented with a rotational vector of energy flux, just like a quantum inductive circuit that has been short-circuited. The energy content within that will create a specific north-south dipole to give us positive or negative charges within that field, as illustrated over on the top right hand side of the page. Obviously, these equilateral geometries can interact via the weak force or the magnetic dipoles that are formed from the energy within their geometry, and these charged mass energies then come together and form larger scale three-dimensional matter. Obviously, as a mass energy geometry, they are two-dimensional and they don't have the property of three-dimensional matter. However, when four of them come together and interact to form a tetrahedral geometry, Obviously it is a three-dimensional geometry, and the net charge of these particles, or these quanta, or the quantum of matter, is determined by the charges of each charged fascia. In this case, we will always result in either a positive or negative charge or a neutral charge. The quantum of matter is the tetration, and you'll see these quantum always denoted, where they're denoted as matter, as T pi. This obviously indicates that it is a geometry that is three-dimensional, and at its heart it is a 4 pi n geometry. As you add more and more tetraons together to form quarks, obviously the net charge changes. In the case of quarks and leptons, they are in fact 12 pi matter geometries, but due to the strong force interaction between their charged fascia, quarks have a distinctly different geometry to that of leptons, even though they are both 12 pi's, and again a distinctly different net charge as a result of their charged fascias. The quarks can obviously, being a non-elemental number, will seek to, through the second law of Tetryonics, to create a stable energy configuration or charge configuration, and in doing so they form the baryons, protons and neutrons and antiprotons and antineutrons. Again, just to point out that the quantum charge, or the quanta of charges within each charged geometry, all add up to create a net charge, and this can be expressed either as a net tetraionic charge with integer numbers, or going back to classical quantum mechanics, we can express it as an elementary charge plus or minus 1 with reference to electrons and protons. Again, Tetryonics shows us that these matter geometries are not spherical, as illustrated on the left hand side. They are all in fact triangular fascia geometries, tetraionic geometries. Obviously, as we increase the mass, or the Planck quanta within each charged geometry or each charged fascia, we're increasing the quanta, or the Compton frequency of the mass energy within that fascia or that charged geometry. It's this mass and these changes of mass energy within the charged fascia that give mass to matter when it is completely stationary. When matter is in motion, the field itself, the mass energy, is added to the chem field, the kinetic EM field of the matter particle in motion. It is not added to the standing wave geometry of the matter quanta. So obviously, in creating various particles, the particles themselves and their mass, as they're normally measured by either charge or mass, or the ratio between the two, is determined by the arrangement of Planck quanta within their charged geometries. In the case of mass energies, two-dimensional mass energies, we refer to them in Tetryonics as mass, or mass energy, and we designate them as n pi, as a two-dimensional field, whereas matter, or three-dimensional matter, is designated again as a tetraionic matter, or T pi geometry. Obviously, these increases of mass energy within the charged fascia give rise to varying mass matters of deuterium nuclei, as illustrated in this example within the atomic nuclei. These increasing energy fields with their equivalent mass content within the matter geometries are also designated within chemistry as atomic shell energies, and it's the transition between these energy levels by electrons that gives us the spectral lines of elements. Obviously, we can through the charged geometries we can create matter as well as antimatter configurations or geometries. and again their net charges are completely determined by the quantum charges of their fascia. As I mentioned, we have rest matter that can be calculated, or rest mass matter, for all particles within Tetryonics. It deviates from classical mechanics where it's a averaged or a weighted mass quantum. We can calculate this because we can calculate the exact mass energy quanta within every charge geometry that creates each particle, and in doing so we've obviously created the mass matter geometry exclusive of any blackbody radiation or any energy of motion, kinetic energy or magnetic moment as well. In the case of chem fields, kinetic EM fields, which are the fields of motion for all matter, when any matter is in motion, in order to accelerate the particle from one velocity to the other, requires the addition of energy momenta into its chem field. This energy is completely stored in the chem field of the rest matter, and this is the mass energy that contributes to the relativistic total energies of particles in motion. Again, this differs from special relativity, and there's a separate lecture on where Tetryonics deviates from special relativity. But obviously the geometry, apart from the math itself, the geometry is different. Tetryonics uses equilateral geometries to show rest mass matter or standing wave geometries, and the energy momenta components of kinetic energy, linear momentum within any measured systems in motion. This has been explained historically using right-angled triangles. In fact, they are all equilateral triangles. Again, as discussed in other lectures, these equilateral energy or chem fields are two-dimensional fields. They are comprised of divergent and convergent energy momenta, and this gives us our familiar law of interaction, where these fields superposition over each other between charged particles or between matter. They follow the standard or the general formula for mass energy velocity, E equals mv squared. Obviously, as we have a standing wave geometry here that would be accelerated, the m refers to the matter that is in motion at a specific velocity. But again, following the Tetrayonic geometries, where we have v or velocity at the top and v squared at the bottom right hand corner, the squared number of quanta to achieve a specific velocity is illustrated in all cases, and it's a direct relationship one to the other. Again, using E equals mv squared, we can take the square root of the energy of the field to determine the linear momenta that's created by that field with respect to the mass that it's accelerating, or the mass of the matter that's being accelerated. Again, we can show this as the relationship between energy and momenta, with momenta being the square of the energy, or the energy being the square of the momenta, or the momentum, linear momentum, being the square root of the energy. In the case of kinetic energy within the chem field, the kinetic energy is the electric permittivity of the field, with the permeability, the magnetic permeability of the field, forming the magnetic moment. In Tetryonics, these two distinct fields are combined as one due to the total energy geometry of the field, and it's titled a chem field, standing for kinetic EM energies. We can then solve, knowing the linear momenta and the energy of the field, we can obviously solve back for whatever mass is being accelerated at that velocity when we know the momentum of the system. Again, as we add more energy due to velocity changes within any system in measurement, or any matter particle in measurement, as we increase their velocity, we have to accordingly increase the number of quanta whether it's increasing or decreasing it. And as we increase it, for example, the geometry stays the same per unit of time, but what changes is the wavelength of the energy quanta within that field. And in fact, length contraction, as referred to in special relativity, should in fact be retermed as wavelength contraction. There is no physical contraction of length in the case of standing wave matter. It is only a wavelength contraction within the chem energy-momenta field. Additionally, as a quick side note, we have a energy field here which we can determine the mass for, and using the rotational vector that you see occasionally within Tetryonics, you can in fact view it as a quantum inductive loop that has been short-circuited, and this loop will resist changes to its energy content. If you try to remove energy, it will use the magnetic field to maintain the electric field strength, and if you try to increase the total energy of the field, it will resist that, just like it does if you were to build a physical inductive loop and short circuit it. In the case of the quantum fields, they're ideal short circuited quantum inductors, so they don't lose energy compared to a classically built model. However, we can use this property of inductance or electrical mass to explain the properties of inertial mass as described by Newton in his three formulas of motion, three laws of motion. And again, in all cases with Tetryonics where we refer to energy and we show the unified equation for energy within any system, we write it as m alpha mu squared. In this case, the m alpha mu by itself would refer to the momenta of the system, so Planck quanta, where the Planck constant itself is mass by quantized angular momentum, which is what the alpha stands for. So Planck quanta refers to the square root of the energy of the energy field, which is the momentum, linear momentum. The quantized angular momentum is the geometry of the field, or the quanta. Or we can refer to the energy of the field as mass, linear momentum I should say in this case, the momenta as mass velocity, again the square root of the energy. Most of Newton's formulations centered around changes in momenta, whereas energy itself is the square of the linear momenta. As we touched on with the wavelength contraction due to the Lorentz factor, we have both a linear correction, as in the case the relationship between the velocity that's created by the energy momenta in the chem field and a speed of c, or the velocity of light, or the natural velocity of energy as Tetryonics refers to it, in a vacuum. Again, this velocity is determined by the number of quanta within the field and its energy momenta of those quanta, all summing up to give us there are divergent as well as convergent energy momenta as illustrated within these fields, but you'll always have a net divergent force resulting from these energy momenta. And in fact, if you add up all these energy momenta closely, looking at the illustration, you'll see that it is divergent. And the relationship between the velocity that's created by these momenta and the natural speed of energy in a vacuum is the Lorentz factor, V on C. We could, of course, knowing that the relationship between linear momentum and scalar energy is the square of the linear momentum, we could, of course, square the Lorentz factor to give us a measure of the scalar energy within the field. So obviously a straightforward Lorentz factor refers to the linear momenta in a system, whereas a squared one refers to the scalar mass energies of that field. And again, changes within the field result in changes in velocity and energy quanta, and they will resist these changes. The current formulation of these has the speed of energy, the natural speed of energy or speed of light, as a upper limit. There is, in fact, when you look at the geometry here, no such upper limit. We can, in fact, keep increasing the energy quanta and increasing the velocity that's resultant from these energy momenta quanta within any equilateral field to any number at all, upwards and onwards, in which case there is not a again, in contradiction to special relativity, there is not a limit of c to velocities, but the equation v on c still applies in both cases. Importantly, what this shows is that Newton's classical velocity addition formula, which was replaced by the relativistic formulas using Lorenz's factors, in fact remains even at relativistic velocities and beyond, or superluminal velocities. This addition is simply the addition of odd-numbered quanta or bosons of charge energy within any scalar energy field. As the odd-numbered quanta in the bosons are added in specific sequential odd numbers to create the square numbers, the energy momenta of those quanta contribute to the net divergent force that's created within any chem field. And again, as more quanta is added to each field, the wavelength, the frequency increases and the wavelength decreases for the quanta themselves. It's a physical change. So obviously, in the case of special relativity, we no longer have an upper limit of c to acceleration, and relativistic formulations no longer need to be used. You can simply determine it straight from the geometry of energy itself or from mass. Obviously, as I mentioned, the momentum of the system is a linear component, whereas the energy or the mass of a two-dimensional field is a scalar measurement of the quanta. Increasing a particle's mass matter, or mass within the matter geometry, increases its total mass. Again, this illustration shows radiocarbon dating, and it's discussed in more detail in previous lectures in chemistry and radioactivity. But to quickly recap, as the energy level is increased within the charged geometries and more quanta is introduced, the mass of the rest matter increases. Historically, this increased mass has been calculated or measured, and then it's been calculated and shown as an additional neutron bound to each one, carbon 12, 13 and 14 in these cases. In reality, there is no additional neutron in these radioactive isotopes of carbon 12. There always remains the 6 deuterium nuclei that make up the carbon 12. What changes is the mass energy content of the charged fascia of the deuterium nuclei, or the matter itself. Obviously, as the mass energy of the carbon 12 matter is increased, any electron that binds to this element will have additional energy inputted into its chem field for the electron. As the electrons are bound, instead of this energy creating a linear velocity for the electron, excuse me, the electron's held in position through the coulombic forces between the protons and the electrons, and the electron is forced to rotate with angular velocity within their fixed positions in the nuclei. This arrangement of the deuterium atom creates a synchronous quantum converter, where mass stored as energy within the charged fascia of deuterium nuclei is slowly radiated away at a set rate via the electrons that are bound to the nuclei themselves. For radiocarbon or carbon-12, carbon-14, we can obviously determine, these are a fixed rate, and we can determine this, and in the case of carbon-12 it's 5,730 years plus or minus. It's a fixed rate due to the quantum release of energy via the electrons, and as it releases it slowly changes back down to quantum level 2 or carbon-13, and then again to quantum level 1, carbon-12. The energy that's in carbon-14 comes from the biological processes of life. It's maintained at this level until the organism dies, at which point it then begins to release. But while the organism's living, energy, black body radiation, thermal energy, maintains carbon-12 at a carbon-14 energy level within the bodies. Again, just looking at the plots of these energy levels, obviously in the case of bosons and photons, it's a linear plot. Again, it's determined by the geometry. They're all odd pi in the case of bosons, but obviously a 79 quanta boson will have more energy than a 3 quanta boson. It's all proportional, again, still through the geometry. All bosons are odd numbered quanta, and they follow the formulation E equals N Planck or H nu. E equals Planck or H nu squared refers to energy levels, scalar fields versus transverse fields. Photons are the same thing, but they're even numbered. They're pairings of bosons. It takes 2 bosons to form a photon. H nu does not equal HF. 2H nu equals HF in the formulations, and again this is something that has to be corrected in the textbooks. A photon is a positive and negative cycle of energy, and again EM waves are formed from photons. So in the case of an EM wave, as discussed in the previous lecture, we will have an even number of quanta made up of pairings of bosons. So an even number of quanta in the field because it's made up of photons, and these photons have 2 bosons to make each photon. As we increase the energy on the charged geometries of all matter, we of course increase their masses in accordance. We can measure this as mass and or energy, and again we just use Einstein's E equals mc squared to relate one to the other. While the mass energy is conservative, as is the charge of any particles that interact, what isn't conservative is the matter. The Tetryonic geometries, or matter geometries, standing waves, are not conservative. You can in fact convert matter into energy and energy into matter. You don't have to have one or the other on both sides of the equation of interaction. And a quick note here, where you see N within Tetryonics, it refers to a specific energy level, which is made up of 1 by 10 to the 19 Planck quanta, or 5 by 10 to the 18 photons. Again, 1 to 2 relationship, and this just gives us, in the case, a scaling between the quantum level at Planck's constant through to, of mass energy, through to the mass energy levels that are common within atomic nuclei. In the case of electrons and onwards, the electrons will have a 1n energy level. Baryons have a 25n energy level. So in the case of a electron, it will be 12 by 1 squared for its base energy level, and the baryon will be 36 by 25 squared for its base mass energy levels in each charged fascia. And it's this difference between energy level N25 and N1 that drives the release of energy by the rotation of electrons within atomic nuclei. As they bind in, the higher energy levels, N25 energy levels of baryons, transfer energy into the chem fields of the electrons and create angular momentum. To clearly define between mass and matter is of extreme importance in quantum physics. It's something that was never done and has failed to be done within within quantum theory itself. And in fact, even in relativity, mass, matter, and energy are all lumped into the one formulation, namely the stress energy tensor, particularly in general relativity. In Tetryonics, as we've noted, we separate them. We define mass with a small m as a two-dimensional energy field that propagates at the natural velocity of energy, or the speed of light in a vacuum. And matter is a standing wave geometry, three-dimensional tetrahedral geometry, as shown at the bottom of the page. In the case of mass energies, the mass and the energy are equivalent, as shown in the unified field equation for mass. They're denoted as n-pi geometries, and because they're two-dimensional, they're measured per c squared to give us the relationship between mass and energy, as denoted in Einstein's equivalence formula, E equals mc squared. The energy field, or this field without the circle, will be a measure of energy. With the time, or the energy measurement per unit of time, we have a c squared field, or measurement area of measurement, in which the energy is measured. That gives us a measurement of mass. If there was no time measurement associated with this field, it would be a measurement of energy. And again, expressing energy, or mass energy, as a density of energy, as is the case in relativity, we can show that mass, small m, is a energy density per square meter. It's a Euclidean two-dimensional measurement of the energy in that region of space, which is completely different to the case of tetrahedral mass energies, or mass matter geometries, where the energy content and the mass content is a measurement of energy density within a cubic or spherical volume region of space, in this case c to the fourth, or a cubic Cartesian coordinate system, or a relativistic system. Mass is related to matter, but they are distinct properties. Two-dimensional mass is a property of three-dimensional matter, with it being the energy content of the fascia. There is no energy within matter geometries. It is all stored as energy in the standing wave that creates the charged fascia. But although mass is a property, or mass energy is a property of matter, matter is not a property of mass energy. You can divide c to the fourth by c squared to give you the mass measurements, but you can't divide c squared by c to the fourth to give you a matter measurement of mass. So again, it's a unidirectional translation. The mass energies of the tetrahedral standing wave geometries are never at rest. They continually propagate through their E fields and M fields, one charging the other within the standing wave geometry. And if you cut out the templates that are available on the web pages and build these geometries, and this is something I strongly encourage that you do as you try to become familiar with Tetryonics, you will see in fact that the energy momenta, specifically the linear momenta of the standing wave geometries, is such that the energy circulates from an E field to an M field, and from an M field to an E field around the tetrahedral geometry. It is a standing wave mass energy geometry in every sense of the word. The energy is never at rest, but the matter that it creates is at physical rest. And again, any changes to that rest matter by way of acceleration, the energy to accelerate it is stored not in the mass energy geometries of the matter, it's stored in the externalized chem field, kinetic EM field of the particle in motion. Again, just to really stress the point, because it is a very important point, from now on within physics and particularly within quantum theory, it is extremely important to replace or carefully word all references between the different properties of mass and matter. Mass is always stated with a small m, matter is always stated with a capital M regarding the physical properties. You may see in the English language where mass doesn't matter, matter doesn't matter, for example, in which case where you refer to the physical property of matter, three-dimensional standing wave energy, it will be a capital M, but the other use of the English word would be a small m. This use of capital M and small m becomes extremely important within cosmology, and as you're trying to differentiate between the radiant EM fields of all matter and the standing wave geometries, standing wave mass energies of those geometries as well, which again were historically lumped together in relativity but have been completely separated within Tetryonics, and from now on great care should be taken when you're referring one to the other within sentences. As we mentioned, any standing wave mass energy that forms rest matter that is accelerated, the energy required to accelerate is stored within the chem field of the particle. It makes no difference whether it's a proton or an electron. The chem field has the same geometry. It will have energy momenta within it, and of sufficient numbers, squared energy momenta, and of sufficient square numbers to create a specific velocity for a specific mass matter arrangement. Obviously, the velocity that's created is related to the momentum of the energy momenta, so if a particle is heavier than, say, a second particle, it will require more energy momenta or quanta to be added to the chem field in order to accelerate it to a specific velocity. But any changes or acceleration, deceleration of the particle results in the release of bosons or changes in the quantum level, as shown here. And again, these quanta are specific odd-numbered geometries, these bosons, the quantum levels. You cannot have a say an energy level of 4 where you have 3 quanta and just add 3 quanta to it. The next addition of quanta must be 5. They are strictly sequential odd numbers down the left hand side of the equilateral energy geometry. Again, you can accelerate, looking at the center of the picture, you can accelerate the particle in either direction to any velocity dependent on the energy quanta, energy momentum quanta within that field. Whichever direction the particle is accelerated, obviously the chem field will point in the direction of motion because the energy momenta is divergent or net divergent, and it's the addition of these energy momenta that give us the linear momenta, or the momentum of direction, the velocity, mass velocity. We can model these obviously using Tetryonic geometries where we just have a circular point charge in the center, and again the chem field that's created has a magnetic moment that is always reflective of the net charge of the particle. And in the case of deuterium nuclei that's illustrated here, all matter will create a magnetic moment or possess a magnetic moment. In the case of deuterium nuclei, it's referred to as a nuclear magneton, whereas the electrons is referred to as the Bohr magneton. Referencing the magnetic dipoles of both the Bohr and the nuclear magnetons together determines whether an electron is a spin-up or a spin-down particle. It is not a physical up or down on the page. In fact, if this deuterium nuclei were upside down to the way it's drawn at the moment, this spin-up, obviously the magnetic moment would be inverted in the opposite direction, and if the spin was in the same direction, this upspin would in fact become a downspin. So just to repeat that, the magnetic dipoles of the nuclear and the Bohr magnetons is what determines whether an electron is an up or a down spin, or a parallel or anti-parallel magnetic moment. And it's probably more appropriate to call them parallel and anti-parallel, because then you can see specifically what is being created. Anti-parallel, obviously it's reversed compared to the nuclear magneton, whereas the parallel has the same arrangement. The parallel has more energy because the similar magnetic poles will repel, so they are storing more energy, whereas the downspin couples and they have less energy. It's a more stable state. Again, quickly to note that the mass energies of the deuterium nuclei, or any nuclear element that electrons bind to, determines the energy of the chem field, or the kinetic energies and magnetic moment of the electron that's bound to that nuclei. Normally this would result in a linear acceleration, obviously, but because the electron's bound to the nuclei, it results in an angular rotation of the electron within the nuclei. As we increase the energy levels of the nuclei, obviously the energy levels of the bound electrons changes as well, or the energy levels of the chem fields of the bound electrons changes. This is normally results in a increase in angular rotation of the electron within the nuclei that it's bound, but this is exactly the same mass-energy-velocity quanta relationship, E equals mv squared, that's present when you accelerate a free electron. It's no difference whether it's free or bound. The only difference that results is that in the case of a bound electron, this energy is doesn't result in a linear motion of the electron. It results in an angular rotation. Again, the mass energies of the geometries determines their mass of the final mass of the particle itself. The charge determines the geometry. The energy content of each charged fascia gives us the mass of the rest matter. Any additional energies above the rest mass energy of the matter geometry is stored in the chem field and results in motion. The differences here obviously is in the case of electrons, positrons versus neutrinos. Neutrinos are at the quantum level, or Planck quanta. They have a single Planck quantum for each charge geometry, whereas electrons and positrons are n-level leptons. Each charge fascia has 1 by 10 to the 19 quanta in each charge fascia, and you can do the calculations just using the unified field equation and dividing it by c squared to give you the mass, and you can see the mass differences between neutrons and charged leptons. They in fact all have identical physical sizes, because the charge geometry is a measure of the time measurement of the energy that creates them. Obviously, as mass is Lorentz invariant to velocity changes. The three main families of particles, the electron, muon, and tauon, or tau families, result from the additional energies or mass energies within the chem fields as a result of their motion. As the electron is accelerated to faster and faster velocities, its rest mass matter remains exactly the same, but what changes is the mass energy content of its chem fields. And again, you can increase up to the tau neutrinos or tau leptons, and likewise you can also decrease from taus back to regular leptons or neutrinos. And in fact, the changing or the acceleration of the lepton family and the changing mass energies of their chem fields is what's classically described within quantum theory as neutrino oscillations. As we mentioned in the case of linear acceleration through the addition of energy, the same thing happens here, where the electron is bound to different energy levels of deuterium nuclei within any element. Obviously, the energy level can be the result of the mass energies of the barrier of the deuterium nuclei itself, or, as we've noted in previous lectures, these deuterium nuclei can in fact act like quantum batteries, in which case when you stack them one on top of each other in a series fashion, it will again increase the angular momentum of leptons that are bound to them. We can obviously create a stylized picture within Tetryonics for photoelectrons with their chem field and rest matter, again noting that the matter and the charge are invariant to velocity changes, but the energy momenta within the chem fields changes in direct proportion to the square of the velocity of the particle. And again, we can measure this energy content within the chem field in electron volts. We can measure it in terms of longitudinal photons, mass energies, or again we can measure it in Planck quanta squared, number of Planck quanta within any energy field. And each squared energy field is made up of odd-numbered bosons. The general formulation for energy within a chem field is exactly the same as that for mass energy. E equals mv squared, different to Einstein's formulation because the more general rule of V is applicable because they don't move at the speed of light in most cases. The other difference obviously is where we're referring to M, we're referring to matter. It's the matter that's being accelerated to that particular velocity, so again you must specify the matter. Where you see matter, obviously mass energy is implied as it's a standing wave. You can, as you'll hear me say, occasionally refer to it as mass matter. It's the same thing. Matter, said by itself, refers to the mass energy standing wave. So in the case of chem fields, we can rewrite the energy as a chem for kinetic EM energies, and mv squared equals Planck frequency in the case of longitudinal photons, Planck quanta squared in the case of the scalar energies, or n Planck quanta, nhv, in the case of where you're specifying the quantum levels that are required to form that energy level. Highlighting, of course, that within Tetryonics, as I've mentioned, we're very specific about mass and matter and energy in all its forms within Tetryonics. In the case of bound electrons, as we increase their energy, we can obviously accelerate them to the point where they break free of atomic nuclei or elements in all cases, the energy level to break free from any periodic element is N8. This is where the Coulombic attraction between the positive charge of the deuterium nuclei and the negative charge of the electron is no longer sufficient to bind it or attract it into a bound position within the nuclei, whether it's a bound within the nuclei or on top of it in the case of a conductive element. These transitions can be drawn in a stylized picture as we've done here to represent the Bohr radius as it was classically described, i.e. transitions between circular atomic electron orbitals within the element. In fact, this isn't the case. The energy is obviously contained within the chem field. It's not that this picture here can be misleading if you're not understanding correctly. It's not the energy contents of the charged fascia. It is simply the energy within the chem field as drawn in the individual pictures. Obviously the color coding still applies for n numbers. N1 has 1 by 10 to the 19 Planck quanta in it. N2 has 4 by 10 to the 19 Planck quanta in it. And if you then calculate these back for photon numbers, you'll see the numbers, or the photon numbers listed here. Or in this case, they're actually quantum numbers, the v squared numbers for the energies. Of course, these energies can be rewritten as electron volts. And obviously, if the maximum bound position, N8, is 13.525 electron volts, and you start at 0.21 of an electron volt, what you have to do is add at least 13.525 electron volts to this 0.211 electron volts, and by doing so, you've accelerated it, or you increased the energy level past N8, and therefore you've excited the electron from a N1 position to an N9 or an N8 plus, and the electron is no longer bound. This total energy then, the sum of these two, about 13.557 electron volts, is then converted from a angular momentum in the bound position to a linear velocity, so the electron accelerates away from the nuclei, and it's then free to radiate the energy it receives in a continuous fashion as opposed to a quantized fashion within elements themselves. Again, highlighting exactly the same thing, the transitions between N1 to N8 as changes of or additions or releases of bosons to create squared energy levels in the chem field. Obviously the square root of these squared energy fields is the linear momentum that it creates in proportion to whatever the mass matter is of the standing mass of the particle. If this was a proton instead of an electron, this amount of mass energy would not accelerate it to the same velocity, because the mass matter is proportional to the momentum. Well, the velocity is proportional to the momentum created by the mass matter and the velocity. So a heavier particle with more mass will not accelerate as much for the same energy as an electron will. Again, noting exactly the same thing, you start at a rest energy level N1 through to 8 within the element. Again, these can be represented in the Bohr radii representation, the classical form. Tetryonics always draws the physical elements, but you can, as a shorthand, still use the Bohr description. Mathematically, these transitions where an electron dropping down levels will emit photons of energy, or where they climb up from the specific energy levels to another, will require energy to be inputted to their chem field. These can be described mathematically, as you see here, with each n level for their eigenstates. You can see them all given here for their energy levels, and again you can calculate for the wave number using Rydberg's formulation. And of course Rydberg's formulation, as we'll show here, is just a measure of the linear momentum of the produced by the chem field for any specific mass-matter geometry. And again noting that in all cases the mass-matter of these geometries remains the same despite the increase of relativistic mass energies to create motion. We can obviously model, as we mentioned before, for spin up, spin down with respect to the nuclear magnetons. We can model protons and electrons. In fact, all matter can be modelled using Tetrayonic equilateral geometries, where we simply destroy the charge in the middle and the chem field is reflective of that charge. This then gives us a quick way of determining magnetic moments, energies, and in fact interactions between particles of differing charges moving in differing directions, or Ampere's law for any physical system. As we noted, the difference in the mass matters, or the mass energies of the charged geometries, the matter, results in different velocities for the same energies because of the differing mass charge ratios between protons and electrons. They have the same but opposite charges, and they have differing mass-matter geometries, and this results in differing mass charge ratios. Again, this is put to use in things like synchrotrons, mass spectrometers, things like that. Again, just as a final note for this page, the spin up or spin down is not a physical manifestation of any particular direction on a page. It is a measure of the orientation of the nuclear and Bohr magnetons. Again, the electrons are stronger than the nuclear one because of the mass charge ratio of the particle itself. The same amount of energy results in a greater velocity and a stronger magnetic moment. Additionally, electrons are quantum rotors in their design, three-phase rotors, so they're far more efficient at generating and utilizing kinetic energies as they move through space or are bound to atomic nuclei. This again highlights the spin orbital coupling of electrons within various elements as they produce spectral lines. Dependent on whether it's a spin up or spin down, or a parallel or anti-parallel arrangement of the magnetic moments for both the element and the electrons, we get differing energy levels produced in the spectral lines. Again, this illustration just shows that where we have a magnetic moment of south-north due to the proton moving in this direction through space, these spins of electrons will produce either a higher or lower energy spin because of the parallel or anti-parallel magnetic moments. And should the element itself change direction, or direction of motion, obviously its magnetic moment will be changed as a result. And the same particles, to achieve the same parallel anti-parallel configurations, requires a change in the spin directions as well. There are in fact 4 different combinations that can produce differing spin arrangements, and these all manifest themselves as hyperfine line splitting, Zeeman effects, etc. As we've noted, the mass energy of the charged fascia gives us the quantum levels, or the principal quantum numbers, for all elements within the Schrödinger wave equation, or as differing atomic shells within the classical description of an element. Tetryonics shows us both the classical as well as the wave formulation, and it shows us in a physical sense what creates this, in this case the mass energy of the charged geometries. Again, this mass energy is part of a deuterium nuclei. It doesn't result in additional neutrons being formed around the atomic nuclei or element. The additional mass energies that are normally accounted for by only having neutral charge generated by protons and electrons is in fact a measurement of the mass energy content. Tetryonics can calculate this because we know the rest mass of every deuterium nuclei at its distinct energy levels, and we know how many are available in each element. So accordingly we can calculate the rest mass energy for this number of deuterium nuclei all at N1 levels, and then as the element builds up with increasing mass energies, we can calculate for this differential, and we can state it as a kinetic energy, as its excess mass energy in a standing wave motion. It is still a kinetic energy. It is stored in a standing wave geometry within the element itself, in its mass geometry. Or we can just term it as it is in chemistry, as chemical energy, the stored energy within the element itself. Either way, adding up the rest mass matter and its chemical or chem energies, etc., will give us a relativistic mass energy for any matter or any element in motion. As we've noted, in this case we've just illustrated the differing energy levels of deuterium nuclei within any periodic element, with energy levels N1 to N8. In reality they are N25 to 32, but the electrons, as they bind to them, have N1 to N8 energy levels, and when they have sufficient energy they can break free. 8 plus will break the electron free of the coulombic attraction of the nuclei. Obviously, if there's a large nuclei with a number of electrons missing, the coulombic attraction is increased because there will be a number of positive charges. The positive charge imbalance will increase in proportion to the number of missing nuclei, missing electrons, so more energy will be required to break these electrons free because of the increase of the positive charge. But in all cases they follow the chem field geometries of kinetic energy, magnetic moments and linear momentum, resulting from their squared energy quanta within those fields. In the case of kinetic energy itself, it's 1/2 of the chem field energy. It's equivalent to the electric field permittivity, and the magnetic moment obviously is equivalent to the magnetic permeability of the chem field. The field itself, the mass of the field, is Lorentz variant, as its varying quanta, squared quanta are required to achieve specific velocities, and in showing this we can also show that the mass of that field is Lorentz variant to changes, whereas the mass of the matter is not. It's already moving at c compared to the velocity of the particle. So all Lorentz changes relate to just the mass energies of the chem fields, not the mass matter, or the mass of the matter. Again, looking at a 1/2 mv squared for the kinetic energies, we can also express this as the square of the linear momenta, the energy, divided by two masses, in this case a positive and a negative, which form the photon geometry, and you can see that here. At the base of this chem field we have divergent positive energy momenta, and at the top of the chem field we have divergent negative energy momenta, but they add up to give us a neutral particle, a chem field, a photon of energy or kinetic energy. And again, as we've discussed in previous lectures, photons themselves can be expressed as kinetic energies. The only difference between a photon and a kinetic energy geometry is the fact that when you're talking about the kinetic energy, or the photons of kinetic energy in a chem field, it produces a unidirectional momentum, or as a linear momentum, as opposed to the bidirectional in the case of radiant photons. As we've mentioned, you can see the changes to the quanta as we add the quanta to varying energy quantum levels. They increase by the square numbers, and again each time we increase by an odd number of quanta, or a quantum level. As the quantum levels added, a specific geometry boson must be added. 3 is added to a 1 to give us 4 squared. 5 is added to 4 to give us 9, which is 3 squared. And again, in the case of bound electrons, this linear momentum that results from the quantized energy momenta of the field is converted into a rotational angular momentum for bound electrons. As we just noted, just to highlight it again, bosons have completely different geometries and distinctly different geometries and properties to photons. Where you have a neutral or a Z boson made up of a positive and negative W bosons, its geometry is completely different to that of a neutral photon, again made up of a positive and a negative W boson. They are identical so far as their mass energies are concerned, but Tetryonics shows them as completely different geometries. In this case, this should have actually been rewritten as it was expressing bosons are described as, the energy content is described as h nu. If we were to refer that as mass, it would be h nu divided by c squared, and accordingly photons are hf. For their energy content, for their mass content, it's hf divided by c squared, with a measurement of time in both cases around them. What does change as a result of their geometry is obviously their wavelengths. Bosons are half wavelength geometries compared to the full wavelength geometries of photons. And again, comparing one to the other in the case of bosons to photons takes 2 bosons to make a photon. This picture clearly shows how bosons come together in quantum numbers, odd numbered geometries, to form the square numbers of scalar energy. And you can see in this case we have 4n pi. It's not a matter geometry. In this geometry, it should in fact probably be best properly drawn as a blue, with the n pi reflective of a two-dimensional mass energy. If these 4n pi two-dimensional fields interact via their weak force and form a three-dimensional matter geometry, it will in fact form a tetrahedral geometry instead of a planar Euclidean geometry, and it will be then a matter quantum as opposed to a mass energy field. Photons are always mass energy fields. As the photons come together in increasing numbers per unit of time, we form electromagnetic fields that are always even numbered. Tetryonic geometries. The photons of 2 pi form even numbers. Applying all this to bound electrons within the nuclei, we can start investigating things like Rydberg's formulation for wave numbers, which still is how wavelengths of light are calculated for, with the transitions between one atomic level and the other, or one n level and the other within atomic elements. In this case, obviously, n stands for 1 by 10 to the 19 quanta again, and it's a square number of the chem field. Remembering, of course, that the n number refers to the energy of the chem field, not the energy of the rest matter. We can use the stylized drawing again of Bohr's radius to summarize all the things that come together that we'll explain shortly. These will be the transitions between n levels and the changes of square energy levels with respect to the matter geometries, what's required to step it from one energy level to the next. Tetryonics shows this as a transition between an initial energy level to a final energy level, Ni, Nf. We can calculate the differential between these quanta that are required for the electron mass matter and determine a differential. Again, it's determined by whatever mass matter geometry you're accelerating. In the case of a proton, electrons are 12 pi, protons are 36 pi, so there's a difference. Again, because you have to account for the mass matter of particles in motion in order to determine how fast they move for any amount of kinetic energy or any number of quanta. Rydberg's formulation has been known for quite a long time now, probably a couple centuries, if not at least 1 century. It's not fully understood what it represents, but it is known that mathematically you can solve this and you will get the wave number, or the number of quanta per unit, per linear length per meter. So X amount of quanta per meter, and again that's just a inverse measurement of wavelength of the quanta. You can invert that and you get the wavelength, or you can apply it through the speed of light, natural speed of energy, which is more appropriate considering it is energy, not the speed of light. It's a specific velocity. So again, wavelength by frequency gives you a velocity. So as you pack more and more quanta in there, you increase the frequency of the quanta, the Compton frequency, and that will result in a decrease of the wavelength, which again has been expressed in other formulations such as de Broglie's formulations. This numbering can be rearranged in a number of ways, and Tetryonics gives an example of each. You can express it as it's expressed in Rydberg's formulation, 1 over an initial energy level of 1 minus 1 over the final energy level 2 squared in this case. You can rationalize it out with basic algebra to give us lowest common denominators. 4 on 4 is the same as 1 on 1, in which case it's 4/4 minus 1/4 gives you 3/4, just as 1 minus 1/4 gives you 3/4. Or in Tetryonics, you can apply it to the physical squared geometries for energy levels 1 and energy level 4. In the case of this, you'll find that there's a fractional release of energy within the scalar Tetrayonic geometry. Again, we'll explain this a lot closer, but you'll see that if you do the math, it's 3/4. But it relates specifically to the quanta of the scalar fields of the chem energy. And again, in all cases, the kinetic EM fields, the chem fields, the kinetic energy of the chem field is half of the chem field, and we can relate that back to HF by looking at the frequency of the light with its relationship to the speed of light, or the velocity of the field, and that shows that Rydberg's is actually a measure of the wavelength, or the linear momentum of the system, which of course, as the quanta increases, the wavelength changes, and the linear momentum that results from the quanta changes in accord as well. They're all related, Tetryonics reveals the exact relationships between all these distinct mathematical properties, something that's never been able to be determined. The math has worked, and it's just been left as a statement that the math works for all these spectral line series without an explanation of why the math works. Obviously, in Tetryonics we state that while mathematics is often described as the language of physics, it is just as appropriate to say that the mathematics is describing the geometry, so the geometry can best be described as the grammar of the language or the math. Where math models what is going on, the geometry shows us physically what the processes are, or the physics of the system. And in some cases it will actually correct erroneous assumptions made from the manipulation of the math without the understanding of the underlying geometry. As I mentioned, we can use the equilateral geometry of the chem field, the energy, along with the mass-energy-velocity quantum relationship, specifically that of frequency, wavelength, linear momentum, all within respect of the geometry shown here, and as has been explained as we've gone through, to give us a clear understanding of Rydberg's formulation. And in fact, it gives, from tetrayonic theory, it will give us an exact number for Rydberg's constant. Again, the transition between these energy levels requires a specific number of quanta in the chem field to be added or taken away in order to create the resultant velocity that will allow the electron to bind to a specific energy level nuclei within the element. Tetryonics, or in tetrayonic chemistry, we obviously were able, using tetrayonic geometry of mass, energy and charge, to create three-dimensional models for all the nuclear elements, all the periodic elements, 1 through to 120. Again, this reveals the atomic shells and the suborbitals, or the 4 quantum numbers, for every electron in every element that's possible. And we can apply this three-dimensional geometry, or charge geometry of matter, for the elements to transitions between these energy levels in shells K through to R, to give us exact calculations for and explanations of the spectral line series of atomic elements. Again, noting that the changes of energy levels require specific odd-numbered boson or odd-numbered quantum bosons to be added in order to create the squared energy levels, and it's the release of these odd-numbered bosons that creates the even-numbered photons that we measure in spectral lines. Again, 2 quanta, HNH nu, gives us 1 frequency, HF. Charged bosons, W plus and W minus bosons, irrespective of how many quanta are in them, come together to form neutral bosons of neutral photons of light. And irrespective of the orientation of the charged bosons, we will always get light photons out. We can calculate using tetrayonics and the squared numbers. Obviously, energy levels 1 through to 8 have squared numbers 1 through to 64, and multiplying for the tetrayonic geometry of the matter that has to be accelerated, in this case a lepton or an electron, we have a 12 pi geometry of the lepton to form an electron, So to accelerate an electron to a specific velocity of 1 through to 8 for the quantum levels, we have to input specific 12n squared quanta to each chem field. In this case, these numbers calculate out to be 36, which is 4 times 12, giving us 48. That should actually be 12 at the top there, not 0. So 1 is 12. 4 by 12 is 48, which is 36 plus 12, and so on through the numbers down to 64 by 12, which is 756 from the top of my head, and off the chart here. In which case 756, if you add together 180, 56, 132, 108, 84, 60, 36 and 12, not 0 as indicated here, add those numbers together for the quanta in the chem field, you'll get the quanta required in the chem field to match the angular rotation, or create the angular rotation for the electron bound to the N8 energy position. Obviously, if we add any more energy, and it would have to be added as another boson, a 17 quanta boson in this case, if we added that 17 quanta boson to these energy levels, we would create sufficient energy in the chem field to break the electron free of the nuclei, or from the element. This specific geometry of bosons, odd numbers again, becomes readily apparent as the mechanism behind the specific energy requirements of the photoelectric effect. You may have a N8 energy level with these bosons in it, but no amount of energy, no intensity at any of these energy levels, 1, 3, 5, 7 or 9, as far as boson energy, will be able to accelerate this electron anymore. It will simply reject those boson geometries. What it's looking for is a specific frequency of boson, or specific odd number of 17 that would then bind into a square number geometry in the chem field to facilitate it breaking free. So it's looking for a specific frequency of light in the UV range to enable the electron to be broken away. No amount of lower energies, red or infrared or whatever, normal light, will be able to break it free, because the normal spectrum range is filled. Again, it's a key part of the photoelectric effect, and this was explained by Einstein, and this is what gave him the Nobel Prize. Tetryonics expands on that theory by showing us the geometry of what is required for the chem field energies. We can represent these specific geometries by simply drawing the changes in the fields. In the case of an N1 transition to level N2 will require 36 quanta to go from a 1 squared energy level to a 2 squared energy level, or 4n. Again, not to confuse N1 with 4n. There are a lot of examples in quantum mechanics where the same letters are used with different meanings, and that's why Tetryonics specifies Planck nu versus Planck nu squared, etc., and n Planck nu, so on, n Planck f. It's done specifically so as to clarify this level of confusion that's arisen over the years. Looking at this geometry, obviously we have energy levels, the transitions between the energy levels, resulting in the various spectral lines of Lyman, Balmer, Paschen, Brackett and Pfund, Humphreys, all result because in the case, for example, Balmer transitions, the chem energies are being released so that it can always transition from a specific energy level back to energy level N2. So it's releasing whatever quanta it has in its chem field to be left with 48 quanta, or 12 times 4 squared, 2 squared, 4. 4 by 12 is 48. In this case, these transitions all have the same geometry for the chem field, as we've mentioned, but as the energy is added, obviously you can see that the wavelength, firstly the frequency, the number of quanta increases, and the wavelength of the quanta decreases in these examples. You can look at this as transitioning down, in which case you release all these quanta in order to transition from a specific energy level down to N2 or N3 or N4, and you see that all of these quanta, as they're released, will have differing wavelengths, and again differing amounts of quanta, different amounts. In the case here, we have extremely short wavelengths for a N8 to N7 transition, extremely short wavelengths, and a small number of quanta compared to what's released in the Lyman, which are infrared. They are longer wavelength quanta, and in the case of a higher energy transition, 8 down to N1, there's more of them. Again, this relationship is unique because of the geometry and the arrangement between odd number bosons adding sequentially to create square numbers within the equilateral geometry, mass-energy geometry of chem fields. And it's this unique arrangement and the geometry that gives us the entire photoelectric effect for bound electrons, along with the specific spectral lines and frequencies of spectral lines and their wavelengths for each spectral line series and the lines within that series. Looking closely at this arrangement, as we said, so far as the kinetic energies or the chem fields of photoelectrons, you can see the physical geometries of the rest matter of the electron along with the chem field as drawn here, again highlighting that they're n quanta changes. In this case, they're not h nu, they are hn, or in the case where it's expressed as quanta, it would be h by 1 by 10 to the 19 squared, as shown over here. 1 by 10 to the 19 quanta equals 1n. Tetryonics just labels it as n energy level transitions to marry up with the marry the electron energy level up with the number of quanta to give a clear definition. Again, you can see that as we transition between energy levels, there are a specific number of quanta that are released for each energy level within the chem field. The chem fields obviously have a mass-energy relationship with velocity of mv squared, matter velocity squared, 12 pi by the velocity squared. These can be written, as we've discussed, in various formats with Rydberg's formulation to solve for the wave number, or the number of quanta per unit of distance per linear meter in this example. We can, knowing the number of quanta, we can obviously take 2 quanta, add them together to give us our frequencies as well. And in fact, we'll show that the frequency that's normally stated should in fact be more appropriately expressed as the number of Planck quanta, because again there is a difference between transverse measurements of energy versus the longitudinal measurements of energy of any chem field. Again, on the right hand side we highlight that the rest matter is a invariant property of the charged geometries, charged mass energies of any particle. It doesn't change with any changes in velocity. What in fact changes when energy is added to the particle to make it move, force, is applied to the particle to accelerate it, the energy of the force is stored in the chem field. It is the chem field, as illustrated at the bottom of this picture, plus the invariant rest matter of the particle that gives us a relativistic mass energy. We term it this way because obviously, in line with Lorentz's formula, Lorentz's factor for the velocity changes, or the changes of energy with respect to the velocity, because of the force that's applied, there is a mass energy change of the entire system. Again, the changing mass energy, the changing wavelengths all occur within the chem field. And as noted at the bottom here, all that energy is stored as photons or bosons, depending whether it's a longitudinal or transverse measurement of the chem field energies. The linear momentum of the system is the square root of the chem field energy and is proportional to the mass and the velocity of the particle, the velocity that results due to the force on the particle. Again, all of Newton's laws, a lot of the classical formulations for physics are all explained along with the quantum formulations of the photoelectric effect and blackbody radiation using Tetryonic geometry. As I just mentioned, transverse measurements of mass energy result in different answers to longitudinal measurements of mass energies. The difference is photons compared to bosons. 2 bosons for every photon. Two Planck quanta for every Planck frequency. These are distinctions that have to be made over and over for those that are new to understanding what's going on and may not have looked at previous lectures. Again, quanta does not equal frequency, except where you have 2 quanta for a frequency. It's an important distinction. You will see in a lot of textbooks Planck's formulation, HV equals HF, equaling the frequency. This is not the case. It must be rewritten in all the textbooks, along with a number of other things that are discussed in Tetryonics, to be 2h mu equals E equals HF. There is a clear distinction between frequency and quanta within Tetrayonic geometries. And again, photons create even-numbered electromagnetic waves because they are multiples of 2 quanta, whereas bosons form quantum levels within energy geometries, and they are odd-numbered charge geometries. Odd versus even at the foundational level. Longitudinal versus transverse at the measurement level. Bosons versus photons at the mathematical formulation of energy. Looking closely at absorption and emission and modeling it with chem fields, we can in fact model the Bohr radius, again using it as a stylized way of representing chem field energy fields, and show in a simplified a schema diagram the relationship between the quanta, the energy transitions, and the spectral lines that are produced by the removal of specific amounts of energy quanta or Planck quanta from the chem field. Tetryonics shows these fields as illustrated here, where on the left hand side we have the energy levels N1 to NX or N8 at the top, then it becomes a free electron. They're color coded as per normal for quantum levels. On the right hand side we draw a line to indicate the initial and the final energy levels where the transition is occurring, so that we can then calculate the precise or the exact number of quanta that must be released to achieve the transition from one energy level to the other. And again, we can use these numbers using Rydberg's formulation, or the Tetryonic equivalent of Rydberg's, to calculate for wavelength, frequency and wave number. for any specific transition of an electron within any atomic element. As a quick example for those that aren't familiar with the transitions that are available, down the bottom of the page here we have an example of a photon of energy striking an electron with a chem field. In this case they're drawn as a linear momentum, but it could also be in a fixed bound position within any atomic nuclei. The photon of wave, the EM wave containing photons of energy, strike the electron and increase the mass energies of the chem field. In the case of a free electron, it's a continuous process. In the case of a bound electron, obviously they have to jump from one square number to another with its chem field energy in proportion to its mass, in this case 12 times, which is where these numbers come from. 12 times 25 squared is 300, 12 times 1 is 12, so the difference between 12 and 300 is a transition of 288 quanta to achieve that. If in this case it's striking, so it's jumping from N1, where we only have 12 quanta, and it's delivering exactly the right quantum levels within the frequencies here, to increase it to a N5 energy level of 300 quanta. So as it does, you'll see that the rest mass matter still remains at 12N in all cases, and the charge, just as importantly, remains at -1 elemental, or a tetraionic -12 charge. What increases through this process obviously is the energy quanta within the chem field. The frequency has increased, the wavelength of the mass energy has been affected, going from a single quanta to 25 squared quanta within the chem field. And as a result of the increased frequency, the velocity changes because of the frequency wavelength change, and of course you've added additional energy momenta to the chem field. These energy momenta result in divergent velocities, or divergent energy momenta. In this case it's a linear one. In the bound electron it would be a increase of the rotation speed of the bound electron, and it retains this. All the mass energy has been added to the chem field. The mass matter remains invariant. It has not changed. At some stage, in the case of an electron, it may give up this photon of light, or in the case of a bound electron, it may be at a higher energy level. N5 is too high and it wants to drop back down to N1, because that's its truly bound position where the coulombic attraction is strongest, so it's pulled back down. When it gets to the N1 level, it releases again 288 quanta from the chem field to change the chem field energies to match its bound energy level. In this case we've done the same thing. It does this by emitting photons of light, or bosons that combine to form photons of light. Again, they're all N levels. If we were looking at this is the EM wave level, you could also express this as nu, positive nu, minus nu, if you were looking at the photons themselves, or the bosons that form the photons. There are a number of ways of looking at these various things. Again, as we say, we can look at the kinetic energy, the magnetic moments. We can look at the quantum levels, or the transverse masses. We can look at the longitudinal photon masses. We can look at the scalar energy of the system. We can look at the linear momentum, or the velocity of the particle itself. And this is what creates such a huge diversity within quantum mechanics and quantum theory. But in all cases, the underlying foundational physics at work is that of equilateral mass energies, or energy momenta. And again, the final part of this page is the fact that the matter velocity squared quanta of the chem field, or the energy of the chem field that's related to the matter, mass matter, through the square of the velocity, is also directly, or it can be quantized, it's probably a better way to describe this. That energy can be quantized via Planck's constant to give us the frequency or the number of quanta, the square quanta, that are required to achieve these changes. We can draw this in yet another way, simply as the spectral series themselves against the n energy levels of the bound electrons. Again, this illustration shows that once you increase the energy level past N8, you have a free electron with continuous spectra, as opposed to the discrete spectra of the n energy levels within atomic nuclei. We can in fact map these lines with relationship to each other and their energy levels, and they'll give us our familiar spectral lines as we see produced with arc lamps in the laboratory, for example. And again, we can relate them all back through E equals hf, or the wavelength of the velocity of propagation compared to the frequency. There's a relationship there. Frequency by wavelength equals velocity. We can also relate it to the energy-momenta quanta of the system as well. And we can solve for all these things using Tetryonics and mathematics. Looking closely at these relationships, obviously we have a matter geometry for all electrons of 12 pi mass energies. That's the geometry of the rest mass matter. And again, as we mentioned, we can solve for the energy of any chem field to determine properties such as wavelengths, wave numbers, one's the inverse of the other, frequency. We can even solve for the linear momenta of the scalar energy, or the velocity that the scalar energy will produce on that particle. And we can use this measure of linear momenta to give us Rydberg's constant. This constant changes dependent on the energy levels, because the wavelength and frequency of the energy quanta for each chem field for different energy levels will obviously change. We can obviously draw these up as a simple chem field geometry, and instead of quantum levels or scalar h nu changes of energy, we can reformulate it through c squared to give us electron volt measurements of energy. So we can see how much precisely in the way of electron volts is required in this case to ionize an electron from a proton in hydrogen to give us a free electron. In this case, we can calculate it exactly to be 13.5259 electron volts to reach energy level N8. So any energy above this 13.5259 electron volts will result in a free ionized electron. In most cases, it's given us 13.6 electron volts. And again, the chem field energy, which was creating a rotational angular momentum of the electron when it was bound to deuterium nuclei in the elements, becomes a linear momentum or a linear velocity for the electron when it's unbound. And again, these chem energies are just energy per c squared, measures of mass, energy, etc. We can formulate for the chem fields as a measurement per unit of time. Without the unit of time measurement of c squared, it is just a energy measurement, as shown here. We can divide it by c squared to give us mass measurements. We can also calculate the specific frequencies of light for transitions, or for, in this case, hydrogen transitions between various energy levels in the hydrogen atom. Tetryonics always calculates these to the extent possible on the calculator, just so we can give the most exact answer, because there are cases where we do a number of calculations based on differing results that are calculated, so we want to use all these results as accurately as possible to give us a clear answer where Tetryonics varies slightly from established theory. Again, Tetryonics will always give us an exact answer in the case of rest mass matters and the kinetic energy of any particle in motion and its blackbody radiation if it's bound. We can draw these transitions as it's drawn here with our raised energy levels of deuterium nuclei, along with the number of quanta that's required for chem fields, for electrons bound in these positions. And additionally, we can draw the additional photons or quanta that are required, bosons that are required even, for transitions from one energy level of a spectral line to another. For example, to jump from Lyman base energy of 1 to energy level 2 requires 36 quanta. To jump from Balmer alpha, you can see the alpha there, alpha 1, say an alpha epsilon transition from energy level 2 to energy level 7 requires 540 quanta. And again, we can label these as transitions or boson additions to the quantum levels, or transitions from one energy level to the other using a number of quanta. The bosons will obviously add up to give us the quanta that's required for the transition, or the total quanta in the chem field, as the scalar chem field is made up of bosons. Again, there will be 12 of each within the chem field because it's matter by velocity squared. So in the case of an electron, it's 12 v squared. Obviously, the changes for transitions between these energy levels can be calculated using h nu, hf, h nu squared, whatever's appropriate depending on what you're trying to measure or determine the energy of. We can do this for every element. Obviously, Tetryonics replaces the Mendeleev periodic table with the Tetrayonic geometry for all the elements. So we can use this knowledge and this geometry to calculate specific rest mass matters, kinetic energies of bound electrons, and the bosons and photons that are released for any transition within any periodic element or any element or compound. Obviously, it's this transition between quantum levels, whether it's within atomic nuclei or within compounds or within elements themselves in the case of hydrogen, that gives us all the familiar spectral lines and in fact all the colours in our universe. Again, looking closely at it, we won't go into a great deal of detail here, but you can look through the picture at your leisure. This picture just simply shows us the up and down spins for the electrons and the chem fields. They are identical. There's no difference so far as the energy levels are concerned. The fine splitting of the lines occurs as a result of the orientation, the up or down spins of the chem fields, the magnetic moment, the Bohr magneton of the electron that's spinning up or down, when it's referenced with respect to the element's nuclear magneton. This picture shows us emissions as opposed to absorptions in the previous illustration, where again it is exactly the same numbers if you compare one picture to the other, which we'll quickly do here. You can see these numbers here. They are all identical to the numbers here. The only difference is, in this case, where the electron gives up the energy to drop down to these energy levels, it releases this number of quanta in the process. In the previous process, it would have had to have had that amount of quanta added to the chem field to facilitate it jumping from the lower energy level to the higher. Again, using the stylized Bohr radius diagram of Tetryonics with the geometry of the electron superimposed, we can use Tetryonics to give us the charge of the particles and the field, the rest mass matter, the kinetic energies, and in fact the total mass energy of the system under study, whether it's in fact the photoelectron or the photons that are emitted. We can calculate and solve for any of them by knowing the Tetryonic geometry. And obviously again, Tetryonics gives us specific relationships between wave numbers, frequency, wavelength and momenta, all being expressed geometrically here on the bottom left hand side. But we can calculate for all of these because we know the number of quanta in any chem field. So by calculating for the transitions and the energy levels or the number of quanta in the chem fields, we can then solve for both the photons that are emitted with their specific energy and wavelengths, and we can then apply that back to give us Rydberg's constant for each spectral line series. And again, Tetryonics will give us exact numbers for both. You will find that Rydberg's boils back down to even a shorthand again, in which we'll relate frequency, wavelength, and wave numbers back to scalar and linear properties of energy fields. This one, again, same picture again, showing us the breakdown between the transitions and energy fields. The difference that this highlights is that the currently accepted value for Rydberg's constant is 109.73731 per meter, quanta per meter. Tetryonics gives us an exact value of 109.03346 per meter. That's the wave number, obviously. The reason for the difference is twofold. One is we obviously know the exact geometries and quanta that's required for these transitions, so we can calculate both the rest mass matter geometries and values along with the exact energy or quanta that's required to facilitate jumps between these energy levels by adding the quanta to the chem fields. We can calculate it as we do here, and we see that it's a factor of the square root of 12 times 8 squared, or 64. Obviously in the transitions we only transition down to N1, we don't transition to 0. So in this case we have to get rid of 63 quanta, and there's 12 charged fascia for the matter. So it's we have to get rid of 756 quanta to transition from N8 to N1, and that's an exact number of quanta. Knowing the quanta, we can then calculate the square root for the linear momenta, which we need because it is the linear momenta that will give us, knowing the rest mass matter, that gives us the velocity for the transition from N1 to N8. In this case it's N8 to N1. So it turns out to be the square root of the energy, obviously. So it's the square root of 756 quanta, and that's what was expressed back here as 27.49545. We'll discuss this number in the pages to follow. But calculating it out, we get an exact value for Rydberg's constant, which we can apply for all the spectral series of lines, and in doing this we can also exclude any excess black body radiation, thermal heat, or any additional energy of motion in any form from these calculations. And this is what's causing the slight discrepancy. Obviously, in taking physical measurements to determine these values, you cannot completely exclude things such as heat and motion of particles from the systems. This gives us a slightly different figure from the purely theoretical number. But again, we can use this purely theoretical number, calculate for it for every spectral line, and the difference will give us a measure of the kinetic motion of the particles being measured, or of the heat of the system, or the black body radiation. As shown here, Tetryonics gives us specific energies for all atomic orbitals. We can show the position of the electrons, we can show their spin up, spin down orientations and energies, and we can calculate for the energies for every atomic orbital and suborbital within any element. We can represent these diagrammatically or geometrically as chem fields for the different different energy photoelectrons, as shown here, N1 to N7. These are the transitions that can take place. Obviously, you can't transition from the final to N0 within the electron. There'll always be a N1. Any electron that binds to a deuterium nuclei will always have an N1 energy level, so you won't have N0 unless it's a free electron and has given up all its chem field energy, in which case it is an electrostatic electron at that point. We can use the square root of these chem fields to give us a number for calculating Rydberg's constant, and you can see this number has been calculated here on this page. Again, these numbers are the square roots of the linear momenta for these energy transitions with the square energy momenta quanta for the chem fields. All the spectral lines can be represented in this manner. Every transition from every energy level, irrespective of whether it's a spin up, spin down, or parallel, anti-parallel, a range of field energy, we can calculate it for it all, and we can obviously draw a representation of the processes and the photons and bosons involved, and that's what this picture here shows us. We can see Rydberg's constant as a measure of the linear momentum of the system, of the field, we can calculate for those numbers either in terms of the linear momenta itself, or in terms of the wave number, the number of quanta per unit length, which gives us the energy momenta of those quanta, gives us the linear momentum. We can show the energy transitions as a circular drawing, in this case, to represent the Bohr's radius. It's not physically one, obviously, but we can then draw on this stylized Bohr radius diagram the various transitions that are possible for every electron within all possible atomic nuclei or elements. We can calculate and solve for the exact number of Planck quanta required to make these transitions between the various energy levels to create the spectral lines. And using these numbers, we can also work backwards to determine black body radiation and additional energy of motion for particles, etc., in excess of these chem field energies. So all the quantum transitions, the quantum jumps that produce spectral lines can be fully accounted for using Tetryonic energy geometries. Obviously, in the case of light that's produced by these processes, the light can superposition once it's been created at a specific wavelength and frequency. These EM waves can superposition with each other to form blackbody radiation, or where more fields of higher energy come together, they can in fact form white light. And it's breaking up this white light created by the superposition fields through a spectrum, or changing the velocity of propagation of the energy by passing it through a medium, that allows us to break it back up into its constituent frequencies and to create spectral images of stars and remote objects, and in fact creates the entire field of spectroscopy. Please note that these spectral lines superpositioned EM fields with white light produced by exciting electrons within atomic orbitals is not the only process that produces white light from our sun. The other process is discussed in more detail in cosmology lectures, specifically stellar processes. Obviously, Tetryonics now gives us the ability to look at EM waves of white light or any color. We can look at the light in terms of all its physical properties of frequency, wavelength, velocity of propagation in a vacuum as well as in a medium. We can look at its mass, its energy, its charge geometry. We can look at its linear momentum as well as its quantized angular momentum, and we can compare the quantized angular momentum to the scalar energy or mass energies of the field to determine properties such as frequency and the number of quanta, the square energies, and the charge of the EM field. Obviously, these all have different units of measurement, but the most important one to take away from this page is the fact that in the case of photons, they have zero rest EM mass, or they have zero matter. They are matterless or weightless particles. The bending of light in gravitational fields due to the presence of gravity is in fact, or will in fact be shown through Tetryonics not to be the bending of light due to gravity. It's an electromagnetic effect similar to the Lorentz force. Photons as well as EM waves are electromagnetic masses. They're shown to have E fields, M fields. In fact, they have a strong photomagneton resulting from their charge geometries of positive and minus charges. And as they contain energy momenta, any measurement of energy momenta per unit of time, in this case 1 second, c squared, will give us an equivalent measurement of mass. If you measure the energy per c squared, you get a measurement of mass, so that's appropriate to say it has mass-energy-momenta. And accordingly, if you measure the equilateral geometry or the quantized angular momentum of the photon, you're creating a measure of the charge. Quantized angular momentum, or alpha per c squared, again is quantized charge. As the charge quanta come together, they form a net charge. In this case, even though we have negative charges and positive charges that create divergent charge fields, these charge fields, in fact, the quanta within them, in fact, equalize out to create a neutral mass-energy geometry. You'll note that I didn't say a matter geometry. It is now appropriate under Tetryonics to refer to photons and EM waves as massive objects, or not so much objects, but massive fields of energy, mass energy. But it's not appropriate to apply that mass as being responsible for the bending of light in a gravitational field. Gravity acts on matter. Matter has a property of mass, but again, mass does not have the property of matter. As Nikola Tesla pointed out, if you wish to find or understand all the secrets of the universe, it's important to think in terms of energy, frequency. In this case, he said vibration. In the terms of Tetryonics, we'd say geometry. Any measurement of the geometry per second, or what passes a point per second, will be perceived to be a change in frequency or a vibration of the energy states of any measured system. Again, all these properties that we've just discussed on the previous couple pages can be summarized as properties of the EM wave's wave function. Again, the Lorentz velocity factors, or the correction factors, beta, are just the result of the energy momenta per chem field. The standing wave matter is Lorentz invariant. It's not subject to changes because it is a fixed amount of mass energy that's circulating at the speed of energy in a standing wave. Whereas the energy or resulting from the force that's applied to a particle to accelerate it is all stored as mass energy within its chem field. So any changes to the velocity of the particle result in a proportional change to the energy quanta of its chem field. And this is where the Lorentz transformation, the Lorentz correction factor, is applied, not to the entire particle as stated in special relativity. As we note here, radiant mass energies, mass, is a measure of energy per c squared, and matter is a measure of energy per c to the fourth region of space. A three-dimensional geometry versus a two-dimensional geometry. To relate mass to matter is a simple process, and it's usually done simply through the spatial coordinate system used to measure the energy. If you take a mass and matter both to be a measure of energy density per spatial coordinate system or per unit of time, you quickly find that mass is related to matter through the square of the speed of light yet again. M equals m divided by c squared. Again, you can rewrite this in terms of energy, and you'd find two different formulations. In the case of mass, you would find that E equals mc squared. There's an equivalence between mass and energy. So again, I'll say that E equals mc squared. Whereas in the case of matter, E equals m divided by c squared. Just to be clear, we're talking about mass in this case. So in the case of mass energy equivalence, it's energy equals mass by the square of the speed of light, E equals mc squared. But in the case of matter, it's E, energy, equals mass divided by c squared to give you the energy content of matter systems. And the difference again is in the spatial coordinate systems used to measure it. The energy in both cases is identical. What you're doing is describing the difference between mass and matter in a mathematical sense in this case. And again, the Lorentz correction factor applies both in a linear fashion, v on c, for the velocity of the particle against the natural speed of propagation for the energy. So in other words, it's like a efficiency factor between how efficiently the energy is moving the matter system compared to how fast the energy would propagate by itself. And we can also express Lorentz correction factors for the scalar properties of the chem field, its mass, its energy, etc. In which case it's V on c squared, quanta squared per c squared. The wave number itself, as expressed by Rydberg's formulation, is simply a measure of how many quanta per linear unit, whereas the wavelength is a measure of the physical wavelength of each quanta, and the frequency is a measure of how many quanta are in the scalar field. Again, they're all directly proportional to one another, and they form the energy of the field, which again is proportional to the velocity of the particle. As we just discussed, all these relationships can be drawn geometrically, and their correct formulations where it concerns mass and matter can be explained at great detail. Again, the chem fields have energy. The energy is proportional to the mass of the matter by its velocity squared. This is the same as this requires, you can quantize this energy through Planck's constant to give you the quanta, or the Compton frequency, and you can take the square root of it to give you the linear momentum of the system, or again mv as opposed to mv squared. Of course, this energy field has a kinetic component as well as a magnetic moment, and as you increase the velocity through the application of force, you increase its kinetic energy and you increase its magnetic moment, but at all times the mass energy matter and the charge geometry of the rest matter remains invariant to these changes, and the Lorentz correction factor does not apply to the matter. It only applies to the chem field. We can obviously express the scalar and linear functions of momentum, wavelength, frequency, etc., wave number, in terms of the quantized angular momentum of the tetrayonic geometry, or the alpha, where alpha stands for the equilateral geometry. Alpha per c squared is the charge. So again, it's showing us that the charge of the energy, the energy quanta of the chem field creates a charge. We can solve for de Broglie's wavelength of these fields simply by dividing the scalar quantized angular momentum of the system by the linear velocity of c, by the linear propagation of energy. Equally, and that gives us a linear function, if you like, the linear component of energy is the wavelength as a measure of its quantized angular momentum. We can also solve for the Compton frequency of the chem field by taking c squared and dividing it by the quantized angular momentum, or the number of quanta. Taking the c squared field and dividing it by the quantized angular momentum, or the equilateral geometries, gives us the frequency. For those of you that are more familiar with this, obviously you'll quickly, and understanding that Planck's constant is a measure of mass by quantized angular momentum, you can quickly say that by putting mass in front of these, you in fact get Planck's constant divided by c, de Broglie wavelength. Compton frequency is mc squared divided by Planck's constant, or energy divided by Planck's quanta. Again, Tetryonics in this case allows us to go one step further than classical physics, or two steps further than classical physics, and another step further than quantum physics, where de Broglie's wavelength and Compton frequency are related. And in fact, we can show the relationship, the linear and scalar relationships of the equilateral geometry of energy to wavelength and frequency. So again, Tetryonic geometry, the alpha constant, will give us the final level of detail, or the geometry of energy in any system. These quantities are all related, as we've discussed over and over. As we increase the system, the energy of a system, or decrease it in this case, transition from N8 to N0, which is the unknown or unnamed spectral transition. We are just changing the number of quanta by taking out a boson of energy. In this case, it will be a boson that has 15 n quanta in it. This will result in the number of quanta in the chem field being changed. So in proportion to that square number of quanta, the velocity that can be exerted through the energy momenta will change in proportion to the matter of the particle being that this chem field is attached to. As we say here, we do this by emitting energy quanta in the form of bosons. They will recombine again to form photons. And again, the formulation is E equals h nu for the bosons, E equals hf for the photons. We can solve for all the properties of the chem field, i.e. the wavelength, the wave number, the frequency, the energy of the field, and we can use the quantized angular momentum of these fields to give us the geometry of all these properties. And again, because the geometry is a fixed geometry for Planck's constant and for quanta, we get specific frequencies, wavelengths, we get specific energy contents, mass, for the bosons and photons that are emitted by energy level transitions. As we noted and touched on before, in quantum mechanics, there's been a tendency since Einstein's equivalency, since special relativity, to state the general formula E equals mv squared as E equals mc squared. Obviously, the c represents the speed of light in a vacuum, or the natural speed of energy. It still remains probably even more appropriate to refer to it as the velocity. So you can in fact cease using Einstein's mass equivalence, where you're not seeking a translation between mass and energy, where you're looking for the velocity that the energy momenta will create from the frequency, or the number of quanta in a field. It's more appropriate to say E equals mv squared. They are exactly the same. They're the same units. The difference is that c squared is a specific relationship, i.e. it specifically relates back to the natural velocity of energy. The difference of one formulation to the other, classical versus relativistic, gives us the Lorentz correction factor, a measure of the efficiency that the linear momentum can produce in accelerating a matter geometry. Again, we can obviously calculate for all these different things, wavelengths, wave numbers, de Broglie wavelengths, Compton frequencies. They're all different aspects of the same equilateral geometry. Again, in most cases we calculate for quanta, but we can also calculate for photons, because we know that it takes 2 quanta to make a photon. So in this case we've indicated the natural distribution of energy in terms of photons. If we didn't want to do it in photons, if it was a transverse measurement, this distribution of photons would become integer numbers, 1, 2 through to 8, and they'd be in yellow, indicating their charged quanta. In this case I've chosen to do it in photons because inevitably we end up measuring the spectral lines in photons of energy, not quanta. There exists a deeper relationship between de Broglie's wavelength relationship for matter waves. He hypothesized in his thesis that the energy momenta of a system, when Planck's constant, or when it's quantized, gives it the property of solidity, mainly because the wavelength becomes shorter and shorter as more energy is applied to a system, as we've discussed. So therefore it gains more mass and has more of the properties of solid matter than it would as a field. This has been interpreted in a number of ways in relativity, etc., and in particularly in things like wave-particle duality. There will be a separate discussion on wave-particle duality in the next lecture. But in this one, de Broglie based his hypothesis on the quantization of energy, and that the wavelengths that are produced have a specific energy momenta content. Tetryonics, now that we've revealed Planck's constant to be a equilateral geometry of energy, i.e. energy per second is mass, the geometry itself is the quantized angular momentum, square meters per second. Again, more of this is discussed in the lecture on equilateral geometries or equilateral energy. But we break it back up. We show Planck's constant h to in fact be mass alpha, and we can show momentum to be mass velocity, or in this case c. We can in fact do this to all cases, and we can in fact show mass to be E equals mc squared under Einstein's equivalence. We could have used V here, but because we're talking about a standing wave of matter, obviously it remains C. If we were referring to the kinetic energy, a chem field, for example, or an electromagnetic field, we would measure it on a chem field. The electromagnetic field again will move at the natural speed of energy, c. So in both cases, in the case of standing wave matter and in the case of electromagnetic fields in a vacuum, the velocity is c. And this highlights where the mathematics was unable to distinguish the subtlety of quantum mechanics from the mathematics, from the mathematical angle. The geometry gives us the velocity relationship, and again shows us that the velocity mv equals mv squared is more appropriate as a general formulation, but in fact it becomes mc squared in the case of measurement of the standing wave mass energies or matter, or in the case of electromagnetic waves or photons, it still remains mc or mc squared for momentum or energy. Again, as we've just discussed, we quantize the energy momenta of fields or matter to determine the de Broglie relationships and Compton frequencies. But if we separate out the mass side of these equations, bring it out as a common factor, we can in fact see that there's a more general or foundational geometry yet again. In this case, c squared divided by a, for those that have done the quantum mechanics sections or lectures, they'll know that is the inverse of charge. Again, it harps back to the amps versus coulombs relationships. But all of the de Broglie relationships are now shown to be measurements of either linear or scalar equilateral geometries. Alpha again standing for the equilateral geometry of energy. Alpha per c squared is the charge, again resulting from the number of equilateral energy quanta within any region of space per unit of time. So we get a extremely low level explanation, again confirming quantized angular momentum and the fact that it's equilateral. And again, we'll apply this in other lectures to explain the fine structure constant and coupling constants, for example, Coulomb's force, as well as charge itself and the role it plays. All of these features apply to photoelectrons, as illustrated here. And in fact, it's the transitions between the chem energies that give us all the spectral lights that we see and can detect, all the colours in the universe. Tetryonics resolves it all back down to the equilateral energy geometry or energy content, mass, of the chem field. And this chem field, as we've said, is the Lorentz factor, is subject to Lorentz corrections due to the velocity of the photoelectron. And it's the energy momenta within the chem field that gives us all our properties of momentum, wavelength, frequency, things like that, and relativistic mass energy, i.e. where the change in mass energy is created as particles accelerate. Again, finally highlighting the fact that Newton's velocity additions remains. Each change in velocity requires a specific odd-numbered boson to be added to create an equilateral or square energy quanta for the field. This continues. You'll see it graphed on many mathematical graphings of the Lorentz contraction for velocity, relativistic velocities, that in fact this energy increases to infinity as you try to approach C. This is not what's happening. There are finite energy levels for all the bosons as you approach E equals mc squared, where the translate the energy efficiency of the linear energy momentum in creating linear momenta for the entire system is a 1-to-1 efficiency. You can in fact increase the 1-to-1 by continuing to add energy to the system, in which case you'll exceed C as a limiting speed. What's being shown here geometrically is the fact that superluminal velocities are possible from the geometric relationship, which again is the foundation of the math, and in fact at the quantum level, right before you reach E equals mc squared for kinetic field energies, is in fact C minus 1. So you'll have C minus 1 quanta in that boson, and you'll have odd-numbered bosons from that number to 1, all adding up sequentially to C squared, just as you do for all other numbers. And in fact, it is the geometry that dictates this relationship between velocity, matter, and momentum, and energy required to create that momentum, and it continues through. So the idea that C is a limiting factor is completely erroneous. It's a result of just plotting the curve and assuming that E equals mc squared, where C is a limit. It is not. It is in fact not a limit. We can, by increasing the energy content of the chem field, we can in fact achieve superluminal velocities. We'll quickly run through these illustrations here. I'll explain the Lyman series in a bit of detail, but you will see that Tetryonics explains all features from a equilateral energy perspective of all the spectral lines that can be produced within any element. On the left hand side you will see the energy level of the deuterium nuclei with the bound electrons. In the case of insulators, conductors have a different electron binding position, but again we accelerate the electron by adding energy to its chem field. The numbers are given in the center of the page, and the field is given at the top right hand side. This quantized field is the field that's illustrated in the center of this right hand side, And again, we show the relationship between quantized energy and photons to that of quantized energy with Rydberg's number per energy level. We calculate for the wave number using Tetryonics, and again this is the exact wave number for the quanta per meter in every transition, and we can apply that to calculate the quanta per meter as indicated in these numbers here, the transitions as we've discussed in depth before. But in each case it is a transition from a higher energy level up to an energy level of N8 down to N1 for the Lyman series. For Balmer it will be the same transition down to N2, and that's the distinction between the various series of lines. Again, in all the cases we will give the energy level of the chem field. We will indicate that the mass, energy and matter geometries, as well as the charge of the particle itself, the matter particle, is invariant to velocity changes, and we will give the energy required in this case to ionize an electron from that energy level. Again, we will give the specific exact wavelength, wave number, frequency, energy and alpha quantized angular momentum, or alpha, for all of these chem fields and their transitions, and the transitions they create. And obviously they're all related to the better known de Broglie-Compton frequencies through the mass quantized angular momentum, or Planck's constant. Again, we've shown before in other lectures how mass alpha is in fact Planck's constant h, and that in turn is in fact the equilateral geometry of energy at the quantum level. You'll see everything is color coded for the transitions, so you can quickly look at these and see the number of quanta. Obviously these numbers of quanta here have to be added up as you transition between differing gaps or differing quantum levels. We then represent these chem fields for these transitions again. As you see here, we've taken it from the previous page with the breakdown for the invariant mass, matter or charge geometries. We've shown the energy content for the chem field, and here we show the bosons or the quantum level geometries of these chem fields as energy measurements. If they were mass, all these equilateral geometries of the chem fields would be exactly the same size. Because we're measuring it in energy, we don't have a binding or a charge geometry that's created, so all the energy quanta are the same size, giving us larger geometries as we go, but the energy is still the same, and the mass is still related to the energy through c squared. But in each case, again, we show the equilateral geometry of Planck's constant as it relates to the linear and scalar properties of the energy of this field to give us wavelengths, wave numbers, frequency and energy. Both sides you have the Tetrayonic version with the mass relationship. On the other side you have the de Broglie equations. We show the absorption as well as the emission in the stylized forms, and we calculate for the specific solutions for all of these properties. Again, looking closely at Rydberg's formulation for these properties of wavelength, wave number, frequency and energy, we look at the kinetic energy fields for the individual transitions that are possible within the spectral line. We then produce a spectral line as it would be detected. Again, normally it's stated that these taper off to infinity with increasing energy levels or become continuous. In fact, this is not the case. There are specific bosons for square energy changes when they're bound, and when they're unbound it just becomes a continuous release of energy. But in fact, by assuming that it went to infinity or became continuous, what was missed was the final spectral line that's available, where there's transitions between N8 and N7 energy levels. Again, we show, and you'll need to zoom in or download the PDFs to get clearer pictures of these, but we show both the Rydberg formulation at the extreme right for the wave number, where we just have 1 over the square of the energy levels that the transition is occurring, levels 2, 3, 4, 5, 6, 7 and 8 in this case. They give us a number. We can also calculate it using the Tetryonic geometry of the quanta, where we jump from level 4 to level 1. Obviously we have to get rid of 3/4 of the energy, or a boson of 3, to go from energy level 3 to energy level 1. We have to get rid of 8 of the bosons, i.e. 8/9 of the energy of the chem field to do this transition. Obviously we have to calculate for the mass by the velocity, or 12 by 9 squared in this case, to give us how many quanta are in the field. But once we do, using Tetryonic geometry, we simply apply this number, and you will see that this number is in fact the same as the number derived using Rydberg's 1 over energy level formulation. The difference being, whilst Rydberg's formulation couldn't be explained either in its straightforward formulation or in the lowest common denomination as to exactly what was happening, Tetryonics gives us the geometry of what's happening in the chem field and the transitions, both in terms of bosons and photons, but specifically in this case in quanta. By doing so, we can view these numbers, or these fractions, as fractions of the renormalized field, or if you take the chem field energy as being 1, or the total energy of the field, these transitions are in fact fractions of 1. 3/4 of 1, 8/9 of 1, 36/34 of 1. And in fact what it shows in this process is that spectral line transitions are fractional changes of chem energies. Again, we've shown with Tetryonic geometry what odd numbers, even numbers, square numbers are, what all the base in terms of irrational numbers, square root of -1, in terms of numbers from positive to negative numbers. We've shown all of the mathematics currently used in maths, including calculus, integration, differentiation, can be represented using equilateral geometries. We also show in this case how we can represent fractions using Tetryonic numbers. We do so simply by changing the energy levels of fields. We can apply this in a number of other ways in quantum computing, as we do, and in fact the entire 5th book of Tetryonics is devoted to revealing the equilateral geometry that forms the foundation of all mathematics. So again, to repeat what I often state, while maths may be stated as being or claimed to be the language of physics, it's now shown that equilateral geometry is the grammar of that language. You can have the math, and without the grammar you will make mistakes. You'll create sentences that do not make sense, and that is what is currently happening in physics at present. There are many cases, as illustrated in Tetryonics, where erroneous physical systems have been described and developed based on purely a mathematical extrapolation using mathematical laws on the numbers that have been measured. Things like multiverses, black holes, extra dimensions, a whole plethora of things where mathematics has been extrapolated into regions that have no basis in physical reality. Our universe is a three-dimensional universe of matter made up of two-dimensional mass energies. There's no additional dimensions, and likely there's nothing. And additionally, there's no such creatures as black holes, etc. We can use the geometry, the equilateral geometry of Tetryonics, to advance our understanding and give us a guide as to how the mathematics should be applied. Hence why I say it's the grammar of maths. And in fact, it will be our guide through all of this, particularly in spectral lines and wave particle duality, which is the next lecture. So we explain here fractional numbers. Obviously, multiplication can be achieved by superposition of fields. Again, the final picture for the series is a summary which just shows the spectral line transitions, or the spectral lines produced by the transitions. And again, in this case, we show it in terms of mass. So we've, instead of the previous 2 pages back where the energy geometries were all the same, we've in fact shown it as mass here, so that the charge, that there's a c squared component that isn't shown, a unit measurement of time. But in doing so, what happens is we can clearly show the final energy level that we're transitioning to, the energy momenta in all the transitions as it changes, which of course determines Rydberg's constant. And we can see the charge arrangement of the charged masses along with the wavelength and frequency relationships of these energy of these fields. Again, we can relate it in physical geometries for the charged fields or Planck quanta, or we can show it in terms of Tetryonic colouring, as we do right beside it. But you can see that in each case we are describing the transition between various energy levels, one to the other. And again, the formulations we've seen on the previous couple of pages are repeated here to show that it is equilateral energy geometries that's bringing it all about. This is again repeated for Balmer series transitions, where instead of dropping down to energy level N1, we only transition to energy level N2. So this of course affects the linear momenta, the number of quanta that need to be released or added to affect the transition, and of course that affects their wavelength and wave number. Again, we represent it in terms of energy fields, or energy quanta more appropriately. These relationships all remain the same, mass being a per second or unit time measurement of energy. We can see the math applied here to give us our fractional changes of the total chem energies. And we see the summarization here, this time using mass or charged masses for the quanta. Again, Paschen series is exactly the same, but the transitions only occur from N8 or unbound electrons down to N3 positions, again affecting the quanta, the number of quanta, the wavelength of those quanta, and their momenta. Again, we represent it in terms of energy, and again we show the fractional math of these energy transitions, and again we show it in terms of charged mass quanta transitioning to N3. Brackett series obviously continues this pattern, and we transition down to energy level N4 within the atomic nuclei. Or conversely, we can add energy and transition up from energy level N4. These are all N-shell transitions, which I've failed to mention as we've gone through, but all the energy levels relate to a specific shell, atomic shell. And again, these are the energy transitions for that spectral series. These are the fractional numbers that relate to the Rydberg calculations. These are the charged mass geometries and arrangements of the energy momenta of the Planck quanta. And in the case, this one is the Pfund series, transitions to N5. Again, the energy changes. You'll note that the wavelengths are getting shorter due to the changing bosons and the higher energy levels. And of course, the linear momenta is changing as well. Fractional numbers are becoming finer and finer, as are the charged masses involved with their mass energy levels. Humphrey's is the second last. Their transitions down to N6. Again, energy geometries. Fractional numbers again becoming finer and smaller fractions still. And charge mass geometries for the chem field. We come to the final one, which I've named Unnamed series. This series has been hidden, I suspect. There's no formal name for it within quantum chemistry or spectroscopy. It's the final fine line. It represents the boson transmission from a N8 to N7 or N7 to N8 excitation. Again, the energy transition. These are, again, bosons are half wavelengths, and the emission of 12 of them form the photons. Extremely fine fractional change of energy here, 0.0047. Again, Tetryonics allows us to calculate this and deem that it is a physical reality, and with a bit of work we should be able to measure these. This particular, it will be, even though it's named a spectral, an unnamed spectral series, because it's a transition to N7, it is in fact one spectral line. It has an alpha line, unnamed alpha, and there is only one transition possible. Any additional energy added to the alpha line above the N7 N8 would result in a free electron. And this may be why it's been hidden, because at this stage the overlapping of Lyman, Balmer series, etc., on top of this unnamed alpha line would result in it being buried below the epsilons and etas lines of the other series. Again, we show the mass geometries. We're releasing this boson, a 15 pi geometry boson, from the energy levels from the chem field to transition down to energy level 7. Just summarizing all of this, as we're at the end of it all now. In the case of all photoelectrons involved in spectral line spectroscopy, or production, emission, absorption, all the energy is stored within the chem fields of the particle in motion. In this case, it's electrons. The energy momenta within those fields are all square quanta, and they're directly related to the velocity that the field is able to create. Again, that velocity is related to the mass matter of the particle through the linear momentum. We can add the relativistic, the rest mass matter of the particle with the Lorentz corrected energies, mass energies of the chem field to give us a total relativistic energy for photoelectrons, exclusive of blackbody radiation, for example. The velocity of the electron in this case results directly from the number of quanta in the chem field at any measured point. Obviously, the process of measuring a field like this would result in energy either being added or subtracted from the field, which explains why Tetryonics is able to get an exact value for Rydberg's constant that's slightly different to the measured values for the measured value of Rydberg at present. Tetryonics calculates for the exact energy quanta as opposed to any additional energy quanta or any energy that's added through the process of measurement. All the spectral lines can be accounted for, including a previously unknown spectral line. We've shown through Tetrayonic geometry that it's the bosons, the odd-numbered quanta, that affect the energy level transitions, and these energy level transitions are in fact transitions between squared numbered chem quanta. The chem field obviously has a kinetic energy component reflective of the permittivity of the field, and a magnetic moment property, again reflective of the magnetic permeability of the chem field. It's a two-dimensional field, and the energy quanta within it accelerates three-dimensional matter. Obviously, the relationship of the energy to the momenta is one of squared energy levels to the square root momenta. mv squared, matter velocity squared, is the energy of the chem field required to accelerate any particular matter to a certain velocity. Matter velocity, or the square root of mv squared, is the linear momentum of the system in motion, the mass matter by the velocity of the particle in motion. So we simply, mv squared will give us the scalar energy, mv will give us the linear momentum of the system. We can apply these formulations to the chem fields. mv squared equals the energy of the kinetic energy, electromagnetic energy of the field, and we can quantize that using Planck's constant or equilateral energy geometries, break it up into the equilateral energy geometries to give us a frequency, or a Compton frequency of quanta. Again, a v squared, nu squared. Nu squared is exactly the same as v squared. There's a direct relationship. Again, using the natural velocity of energy, we can convert Rydberg's constant from frequency to wavelength to wave number and show it's a measure of linear momenta. This picture gives us these relationships in a single geometry reflective of the energy of photoelectrons, or bound photoelectrons within the atomic nuclei. Again, mv squared, the mass velocity, the momenta, and the mass velocity squared, the energy of the field, are related to each other through the geometry. And transitions of the energy field of the photoelectrons, probably better to explain. The transition of photoelectrons from one energy to the other requires additional quanta, as the frequency of the quanta increases, the wavelength decreases. And we can express this again using Rydberg's constant to calculate for wavelengths and wave numbers. Again, we can re-summarize all of this using the stylized version of the electron superimposed over the Bohr radius. Again, it's not the physical relationship between the charge geometry of an electron and its chem field. It's just a stylized version for easy reference. The energy that's pictured on the side of these fascia is in fact stored in the chem field of the electron. But using this, we can show all these relationships in a quick cheat sheet, if you like, for every single spectral line. And we can use this along with the square root of 256 to give us all the properties of photoelectrons within elements. We can apply all this knowledge, obviously, to the photoelectric effect as described by Einstein, and we can show not only how there are key boson geometries required for transitions between energy levels, as well as sequential bosons required to transition or jump from one energy level to the other. For example, to go from N4 to N8 without being in between, to just jump immediately to N8 would require a specific number of photons of a specific wavelength and frequency. Obviously, it would be a case of adding 9, 11, 13 and 15 together to calculate to show the geometry, calculate the Compton frequency, and from that we can get the wavelength, wave number, etc. that we've just done in the previous exercises. But it does show that there is a specific frequency of light that will facilitate this transition or break the electron free, ionize it, continuing to apply energy at the wrong frequency, or increasing the intensity of the wrong frequency light will not result in the electron having sufficient kinetic energy to break free. The wrong frequency or wavelengths of light, no matter how high the intensity, will be rejected. There are specific wavelengths, frequencies, and quantum number required for every transition in every atomic element. And this is what's made it so hard, without an accurate 3D model of the atom itself and these chem fields and the energies, for us to be able to calculate the exact spectral lines for increasingly large or heavy elements. We can calculate for the basic elements for straightforward transitions, but when we start doing things like sodium or uranium, it becomes incredibly complex and can't be done. Tetryonics gives us the ability to do that. Obviously, the wavelength of any energy that's required to ionize these electrons in the photoelectric effect per unit of time will have differing quanta and differing wavelength and frequencies, differing energy momenta as a result of these relationships. We can apply this to all the elements. In this case, we've done it to sodium, and not only can we show the preferred energy levels where they excite electrons from bound positions to their free or positions or anything above energy level 3, we can also show how many electrons will be emitted for specific frequencies of light based on their quantum energy levels. Obviously, we can release far more energies by adding specific photons to sodium if we excite the Balmer series from energy level N2 higher. If we excite energy level N3 or N1 to their ionization levels, there are far less bound electrons in those positions. Obviously the binding's stronger for these energy levels, so more energy is required to break an N1 free compared to an N3. N3 being the valence ones. They will ionize rapidly, but with the appropriate frequency and energy, again wavelength, they're all related, to transition from N2 to N4 or more, we will have far more electrons ionized, because there are 8 N2 electrons for every N3, and there are 4 N2 electrons for every N1 electron. So obviously, even though it requires more energy, we would liberate far more ionized electrons by calculating for an N2 to a N4 plus transition than we would for an N3 to an N4 plus transition. In fact, we would release 8 times more electrons. Again, this is just repeating what we've said, that mass, EM masses, are related to Planck energies through the equilateral geometry of energy and how we measure it. Matter and photons, as well as Planck energies and bosons, are all charged geometries in Tetryonics, and that as we add energy to any system or any EM wave, we affect the frequency of the wave, we affect its wavelength of the quanta within the wave, or the photons, and we affect the energy momenta of the wave itself. Although, note that here in Tetryonics, where we've been able to recalculate the standard frequency wavelength relationship, which is normally related back to the velocity of energy, or c, Tetryonics states it as v. Again, a velocity. It's exactly the same as c. It's just a generic formulation for velocity. In this case, we specify it as velocity of light or of energy. Again, it's done that way because this may change if it's a measurement in water or through glass, for example. Different mediums produce different velocities. But in all cases, Tetryonics shows that the frequency is a scalar measurement of the quantized or the equilateral energies, whereas the wavelength is a linear measurement of this energy. So we have mass momenta, wavelength frequency, c squared. All these relationships are related back through the velocity, and we show that clearly here. In this case, the velocity of light, when you solve this equation for frequency wavelength using equilateral geometries or alpha, you see that you're left with c. Alphas cancel out. C squared divided by c is c, and this is why the equilateral geometries remained hidden within the mathematics. We've never had this level of detail available in the math, whereas the geometry gives us this level of detail and shows us how this relationship comes about, how frequency and wavelength create the velocity of light in EM waves. All of this we represent in Tetryonics. In summarizing all of this, we represent using Tetrayonic geometries, again, mass geometries, charge geometries. We have two-dimensional kinetic fields, chem fields, with kinetic energy and magnetic moments. And it's the relationships of all these, of the quanta within these fields, the squared number of quanta, that give us the linear momentum and velocity of particles. Again, all of this has a major impact on relativity theory, and in fact it completely rewrites the foundations of relativity, special relativity, in doing this. Again, n Planck nu refers to the boson energy levels. Planck nu squared refers to the scalar energy, and the square root of the energy is the linear momentum. In all cases, no matter what the acceleration is of the particle, the mass matter of the particle itself is Lorentz invariant, and all the Lorentz corrections are applied to the mass energy of the chem field. The final question this brings up, obviously, now that we know the difference between bosons and photons, between mass, energy and matter, and the geometry that equilateral mass energy can create through its relationship of charge, or its alpha per c squared. What it allows us to do is use the equilateral geometry of photons and bosons and energy itself to show the difference between waves and particles. And one of the last remaining questions in quantum mechanics, particularly quantum electrodynamics, is this problem of wave-particle duality, where properties that should be described or can be described as particles, photons, can in fact also be described best through interference patterns that they produce as waves. The lecture for spectral lines has been completed up to this point, and this is where we'll finish it, but the next lecture is on wave-particle duality, and we will show using the equilateral geometry of energy, specifically that of photons and chem fields with photoelectrons, how the equilateral geometry of energy explains wave-particle duality and clears up all the misconceptions that have occurred historically with quantum mechanics and quantum electrodynamics. This has been a long lecture. I thank you, those that have managed to persevere through to the end. If you have any questions, obviously feel free to email me with any specifics, and I'll be only too happy to answer. If not, obviously feel free to download the PDFs themselves and the templates and make these physical models of photons, bosons and chem fields along with the matter particles of electrons. Again, thank you for the time and your perseverance on this rather difficult subject.